you've got phony letters, when you replicate your DNA, it's going to have a lot of phony letters in it, and the cell's not going to know how to read it or what to do with it. We'll talk more about this when we talk about viruses. But there are enzymes that we can use to inhibit the manufacture of DNA or the manufacture of RNA. So if we give the patient a drug that causes their bacteria or their viruses not to be able to replicate their DNA or make RNA, that's how we hurt them. Summary: 2 ways to interfere with nucleic acid synthesis. Use drugs that act as base analogs, so you have imposter building blocks, or interfere with the enzymes needed for DNA replication or RNA manufacture, or RNA synthesis. Prevention of virus attachment, that's about viruses. Okay. I'm looking for spectrum of action, but I'm not seeing it here. It'll come up. Okay. Antimicrobial drugs. What do you want? All the good stuff. And here's spectrum of action. So antimicrobial drug, you want to be able to get it. You don't want it to be too expensive. You want it to be chemically stable so it can last on the shelf and also persist in the body and get to the site of infection. You want to be able to administer it relatively easy. Give my patient a shot or take it orally. If it's too hard to administer it, what good is it? And you don't want it to be toxic or allergenic to your patient. And you want it to be selectively toxic so your patient doesn't get sick. But theoretically, we want to be able to get a lot of bugs with it too. So there's different things you would want to consider when you prescribe an antimicrobial. If your patient has a mixed infection, multiple microbes in there, you want a broad spectrum antibiotic. Maybe your patient has one kind of bacteria, a very specific kind. Why would I give you a broad spectrum antibiotic that's probably going to hurt your normal flora too, if I can give you an antibiotic that's selectively toxic, will specifically target just that one species of bacterium? So that would be narrow spectrum. Broad spectrum covers a wide range of pathogens, including gram-negative and gram-positive. Narrow spectrum specifically targets one particular kind of bacteria. There's 2 ways to go, depending on what's going on in your patient. If you don't really know what the infection is in your patient, but you got to do something, you might give them a broad spectrum. Or if you know your patient has a mixed infection, it's a UTI with gram-negative and gram-positive, give them a broad spectrum. If he's got something like tuberculosis, you're going to target that specific organism. That would be narrow spectrum. So that's the spectrum of action of the drug. Narrow and broad spectrum.
Professor?
Yeah.
And just to, I guess, illustrate that effect, I had a patient who had Klebsiella and MRSA at the same time. So we would do IV Vanco for gram-positive and IV Rocephin for gram-negative.
Right.
Treat them concurrently.
Yeah, good, because the Klebsiella is gram-negative and the MRSA is gram-positive. And the problem is there when patient's got a mixed infection like that, and he's probably immunocompromised, which is why he got a mixed infection in the first place. It's really hard for the body to deal with all that at the same time. And so and actually what they did was, that was pretty targeted. That was actually a pretty specific treatment that they gave. Narrow spectrum Rocephin for the gram-negative and narrow spectrum Vanco for the MRSA. But a lot of his normal flora is getting killed there too, which makes his immune system weaker even, So you really got to count on the antibiotic to get those infections, because his immune system's not going to be a lot of help. Spectrum of activity. So here they're showing you, for example, isoniazid will cover mycobacteria and some gram-negatives. So that's how that figure works. Broad spectrum, a good example of a broad spectrum drug would be tetracycline. Tetracycline is our classic broad spectrum antibiotic. Tetracycline targets ribosomes. Gram-negative cells have ribosomes, gram-positive cells have ribosomes, even chlamydia and rickettsia have ribosomes. So it's your classic broad spectrum because it targets ribosomes that all the bacteria have. Problem, I have ribosomes in my cells too, so I might have some side effects with tetracycline, but it's a good broad spectrum drug. Everybody seems totally bored today. Are you okay? Yeah. Sam's having trouble even keeping awake. He had a difficult experiment this morning. He had to wait forever for his auger to melt. This is what your plates are gonna look like when you come back on Thursday, and you're gonna measure the zone of inhibition, which is all the way across. Can you see the little cursor all the way across? So you're gonna turn your plate upside down. You're gonna hold your ruler up to the bottom of the plate, so you don't have to open it, just turn it upside down, and you'll see those clear zones around the discs. What's happening here? Zone of inhibition, no bacteria growing, right? What's happening here?
Nothing.
Nothing. What does that mean?
The antibiotic's not working.
The antibiotic's not working. These bacteria are laughing in its face. They're having lunch on it, right? They're growing right up and onto the disc. You can't see them growing on the disc because you're looking at the underside of the plate, but if you're looking at the top, you would see the bacteria growing right on the disc. The bacteria are completely resistant to the antibiotic in that disc. What if we compare this antibiotic in this disc to this antibiotic in this disc? Which one has a stronger effect?
Oh, the bigger one. The bigger one?
You naturally would think the bigger one, and you're probably right. However, antibiotics are chemical molecules. Some are larger than others. Some will diffuse into the agar faster than others. So these might actually be the same effectiveness. It's just that this one diffuses into the agar faster, so you get a bigger ring. So they actually have charts and tables, and you'll see it on the antibiotic chart for you to use at the bottom. There's like a scale where you can gauge. For this particular drug, a zone of inhibition this many millimeters across might be considered not sensitive. The bacteria are not sensitive to it. They're resistant. And this one, even though it's a smaller zone of inhibition, the chart might say, well, this is a larger molecule, diffuse a lot slower. The bacteria are actually sensitive to this one and resistant to this one. So it's not enough just to eyeball the zone of inhibition. You have to measure it and compare it to a standard chart of known measurements that indicate sensitivity and resistance for each different antibiotic. So on your page that I typed up for you, you have a tiny little chart. But these charts are like, there's like an entire book of these charts for all the different antibiotics. But in general, a larger zone of inhibition would reflect higher sensitivity of the bacteria to that particular antibiotic. So if this is a pure culture of E. coli are probably more sensitive to this antibiotic than they are to that one. That's not enough to pick an antibiotic. They all